Okay, sixth graders, we are going to be reading today about heat transfer. It's in the textbook, pages 42 to 45. And this section is really going to help us build this foundation for how heat is actually moved around in the troposphere, which will really relate in our next unit about wind and weather in particular. So, this is really an important section here. So, we are going to start out on page 42, heat transfer. We're going to skip this little activity here, but we're going to start going down here. So if you would open your book, follow along with me. I will potentially be doing some drawing on here or marking on here, pointing some things out. We'll see where we go. So here we go. You pour a cup of steaming tea from a teapot. Your teacup is warm to the touch. Somehow, heat was transferred from one object, from the cup, to another, your hand, that it was touching. That's an example of conduction, one of the three ways that heat can be transferred. As you'll learn in this section, heat transfer in the troposphere plays an important role in influencing Earth's weather. Whenever I think of the word conduction, I always think about touching, and conduction is something that is used in electricity. But in order for electricity to flow through something, it has to be touching, and it's conducting electricity. So we always remember conducting is by touching. So that's one of the ways that heat is transferred in the troposphere, and we're going to learn about the three ways. Thermal energy and temperature. And before we go on, what you'll notice here is you have this cup of iced beverage here. Maybe it's an iced a tea with a lemon there, and you can see the molecules. And then you have the hot tea over here, and they show the molecules. And what they're showing you, they're visualizing, is that the hot tea, those molecules have more movement because they have more energy. It says the iced tea is cold, so the molecules move slowly. The herbal tea is hot, so its molecules move faster than the molecules in the iced tea. And that's going to be a little bit of an important concept as we go on. Thermal energy and temperature. The tea in the cup and in the teapot, they're the same temperature, but they have a different amount of total energy. And the tea in the cup and the pot they are referring to are right here. So you see the tea in the cup and the tea in the pot. They might be the same temperature, as they said, but they have a different amount of total energy. To understand this, you need to know that all substances are made up of tiny particles that are constantly moving. We've talked about atoms. The faster the particles are moving, the more energy they have. Figure 4 shows how the motion of particles is related to the amount of energy they hold. Temperature is the average amount of motion each particle of substance. So what they're showing you is that temperature up here is really just an average of how much thermal energy the molecules have together. So if you added up all the energy of each of the atoms and took the average, you would have a lower temperature than you would here if you took all the energy of all the atoms, added it together, because each atom has more energy, and took the there. So the temperature is the, as they say here, temperature is the average amount of energy of motion of each particle. Okay. So temperature is just how hot or cold a substance is. Okay. In contrast, the total energy of motion in the particles is called its thermal energy. So while temperature is an average, so you take your temperature, you get 97.6 or whatever, that's really an average. Some atoms may have greater energy, some may be less, but it's an average, okay? Thermal energy is a total amount of energy of all the particles of a substance. So going back again to the teapot and the teacup, they both actually have the same temperature. But because the teacup has less molecules, it has a lower thermal energy. It says the hot tea in the teapot has more thermal energy than the hot tea in the teacup because it has more particles. So while it may have the same temperature, the teapot will have more thermal energy because it has more particles. Okay? Here, measuring temperature. Well, we've talked about this before. Temperature is one of the most important factors affecting the weather. Air temperature is usually measured with a thermometer. A thermometer is a thin glass tube with a bulb on one end that contains a liquid, usually mercury, which we know we don't use anymore, or colored alcohol. Thermometers work because liquids expand when they are heated. Those particles have more energy, and so they spread out more because they're moving more. They take up more space. They expand when they're heated, and they contract when they're cooled. When they're cooled, they're moving less. They take up less space, so they contract. When the air temperature outside increases, the temperature in the liquid bulb also increases. This causes the liquid to expand and rise up in the column, which shows us there's been an increase in the temperature. Now, we've talked about a couple of temperature scales before. Temperature is measured in units called degrees. There are two temperature scales commonly used. We have talked about the Kelvin, but mostly we use the Celsius scale and the Fahrenheit scale. In science, we mostly use the Celsius scale. On the Celsius scale, it's really nice because the freezing point of water is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. So they are nice round numbers to remember. But weather reports in the United States use the Fahrenheit scale. On the Fahrenheit scale, the freezing point of water is 32 degrees Fahrenheit and the boiling point is 212. And I remember when I was little, if I used to think, well, if 100 degrees is boiling and I have a temperature that's over 100, how is my blood not boiling? But it's because we take our temperature in Fahrenheit. And so in order for my blood to be boiling on the Fahrenheit scale, it would have to be above 212 degrees. So heat is transferred. How heat is transferred? Because heat can be transferred from one object to another, and there's a couple of ways. Heat is the transfer of thermal energy from the hotter object to a cooler one. If I put my hand on my forehead and my forehead feels warm, that is heat. I feel it as heat. It is transferred from my head to my hand. So it can be transferred in three ways: radiation, conduction, and convection. And we're going to learn about them. Radiation is usually the trickiest one. And it says, have you ever felt the warmth of the sun's rays on your face? You are feeling energy coming directly from the sun as radiation. Recall the radiation is the direct transfer of energy by electromagnetic waves. Electromagnetic waves meaning they can travel through the vacuum of space. They don't need atoms or molecules to travel. The other two ways that we're going to talk about, conduction and convection, they do need atoms and molecules in order to transfer heat. But radiation is the only one that can travel through the vacuum of space. Most of the heat that you feel from the sun travels to you as infrared radiation. You cannot see infrared radiation, but you can feel it as heat. And yes, there are special cameras made so that you can see infrared radiation. Conduction, we talked about at the beginning of the reading. Have you ever walked barefoot on hot sand? Your feet feel hot because heat moved directly from the sand into your feet. The direct transfer of heat from one substance to another that is touching is called conduction. So when a fast-moving sand molecule hits a slower-moving molecule on your foot, the faster molecule transfers some of its energy. Your foot absorbs some of that energy and it feels hot. The closer together the atoms or molecules in a substance are, the more effectively they can conduct heat. Conduction works well in some solids, such as metals. Metals are really good conductors if you've ever been cooking with a metal spoon or have it in a hot thing, but not that well in liquids and gases. Like air and water do not conduct heat very well. They're not good insulators and they don't hold the heat very well. Convection is the majority of the way that heat is transferred in the troposphere. So this is a little bit of this is the most difficult concept, I think, to understand. But basically, in a fluid is any substance that can move that's not in a stable position. So those are liquids and gases. In fluids, particles can move easily from one place to another. And as they move, their energy can go along with them. The transfer of heat by the movement of a fluid is called convection. Now, it's a pretty simple explanation there, but we're going to talk about how that works in a minute. Heating the troposphere. Radiation, conduction, and convection work together to heat the troposphere. During the day, the sun's radiation heats the Earth's surface. The land becomes warmer than the air, and the air near Earth's surface is warmed by both radiation and conduction. And I'm going to do a little diagram here for us. Let me grab my colored markers here. Bear with me. Okay. So during the day, what you get is you get the sun over here. You get the sun's rays, right? You get them heating up the Earth, okay? Here is the Earth. Here, okay? So what happens is the sun's energy comes down and it heats up the Earth, okay? This is radiation. Wow, a little blue ink there. So this is radiation, okay? That sun's energy will travel down there. Then what happens is it says here, during the day, the sun's radiation heats the Earth's surface. The land becomes warmer than the air. Now, the air near the Earth's surface is warmed because some of that heat will radiate up, okay? But also, what happens is these molecules that are close, they'll touch the Earth. And because they're touching it, they will gain some of that energy from touching Earth's surface. So some of them gain it just from the heat being radiated up. Some of it gain because those molecules actually come in contact with Earth's surface. So we also have heat transfer at Earth's surface by touching or conduction there. I'm not sure if you guys can see all of that right now, okay? So we've got those two things happening. So we've got heat transfer from the sun by radiation, touching Earth as it warms Earth's surface. Some of that heat will radiate back, but any molecules that actually touch Earth's surface are warmed up by conduction, by touching, okay? However, heat is not easily transferred from one particle to another by conduction. Only the first few meters of the troposphere are heated by conduction. So that doesn't do a really good job of heating our whole troposphere. If only the molecules close to the surface can touch it, that's not going to warm up a lot of the troposphere. So what happens is, as those molecules, it says only the first few meters of the troposphere are heated by conduction. Thus, the air close to the ground is usually warmer than the air a few meters up. However, within the troposphere, heat is transferred mostly by convection. And this is what happens. When the air near the ground is heated up, and we've talked about what happens when you heat gases. When the air near the ground is heated, its particles move more rapidly. As a result, they bump into each other and they move farther apart. So close to down here, as these particles heat up, they begin to move more rapidly and they expand. They become less dense. And that air, as it heats up, will rise. Those particles are moving apart. As it says, as a result, they bump into each other and they move farther apart. The air becomes less dense. What happens then is you get this colder, I think it's green, I should have worn that. The colder air then will move in to take its place because something needs to fill that space. So that cold air is more dense. So it says cooler, denser air sinks towards the surface, forcing the warm air to rise. The upward movement of warm air and the downward movement of cool air form convection currents. So I'm going to use red and blue here. So the warm air, as it will rise, okay, and then the cool air, I'm going to erase my green here, and then the cooler air will come in to take its place. This forms a convection current. And that is really how most of the gases in our troposphere get heated, okay? The upward movement of warm air, underline it here, the upward movement of warm air and the downward movement of cool air form convection currents, okay? Convection currents move heat throughout the troposphere. And this diagram on the next page really does a nice job of explaining what I just drew, basically. So here again, we have our heat transfer by the sun. This is radiating down, okay? So that's radiation. Some of that heat will, again, radiate up. It will just, the electromagnetic, the heat will just radiate up. But anything that comes in contact with the ground, air molecules, your feet, those objects are heated by conduction, okay? Because they're touching, all right? As those gas molecules near the ground begin to heat up because of touching, they will gain energy and they will move more and they will expand and spread apart. So as they spread apart, they become less dense. The cooler, denser air will sink and take its place. And so you get this movement of warm air rising and cold air sinking, and that causes a convection current within the troposphere, and that is mainly how the convection currents are formed. And here's another diagram here showing you. So radiation is just that heat radiating it out. It doesn't need touching, and it's not the movement of air or liquid. Conduction, the pot is right here touching that electric coil that's been heated. So they are touching, and that's conduction. Now, these water molecules on the bottom are touching the pot, and they begin to heat up. As those water molecules heat up, they will become less dense and they will rise. And then the cooler water will sink, and that is by convection. That is a convection current. So I hope that helped you guys understand radiation, conduction, and convection. Good luck answering your questions, and we'll be exploring this in some labs.